Okay, here's our last two questions. And question 9 has two parts, a part A, a part B. So there's really two equations to solve. The first one there's not much to do, but I put it in there anyway. Um, and so it asks us to solve log base 4 of 1 over 64. So we want to know if we can write 64 with a base of 4. And we know that 4 squared is 16. And so we see, well, what happens if we multiply 16 by 4, or if we multiply one more 4 then by that product. And 16 times 4 is 64. So that tells us that 64 is 4 cubed. So we write this 1 over 64 as 1 over 4 cubed. And we use this property of negative exponents that says if we change the sign of this exponent and bring it to the numerator, then that's the same as having it in the denominator with the positive exponent. So that's log base 4 of 4 to the negative 3 now. Well, when we have a logarithm of a particular base taken of that same base, then those two operations cancel one another out, and that just leaves the exponent alone. And so that gives us our solution of negative 3 is equal to x. Now in part B, we will use a different property of logarithms. We have two logarithms with the same base, log base 3 of x and log base 3 of x plus 6. And there is a sum here of these two logarithms. Well, we use the product rule that tells us that when we have two logarithms with the same base added together, that's the same as, that can be compacted down into one logarithm with that base of the two arguments, that's what those are called, multiplied together. So we multiply x times x plus 3, and that's what we're taking the log base 3 of. And x times x is x squared, x times 6 is 6x. So we have log base 3 of x squared plus 6x. Now we convert this to its exponential equivalent. And to do that, we remember that this 3 here is a base. And we sort of cross out the log, and we bring this 3 over to this side of the equation as the exponent of this base, and we bring this argument to the other side of the equation. And so log base 3 of this argument equals 3 is the same as 3 raised to the third equal to this argument. Well, 3 cubed is 27. And when we subtract 27 from both sides, lo and behold, we have a quadratic. Well, here we had a quadratic equation, but here when we subtract 27 from both sides, we have a quadratic trinomial, and when we factor that, our two factors are x plus 9 and x minus 3. So the solutions to this equation, not this equation, not the logarithmic equation, but the solution to this quadratic equation is negative 9, because if we put a negative 9 here, negative 9 plus 9 is 0, and 0 times anything is 0. And positive 3, because if we put a positive 3 here, 3 minus 3 is 0, and 0 times anything is 0. So those are the two possible solutions. They are not the two solutions of this original equation. They're merely the possible solutions of this original equation. And so we check to see if these, we check in the original equation if these are viable solutions. Well, if we put log base 3 of 3 here, we know that's 1, and 3 plus 6 is 9, and if we put log base 3 of 9, that gives us 2, and 1 plus 2 is 3, so that solution works. But when we put negative 9 here, we see immediately we will be taking the logarithm of a negative number, and that we cannot do. So we cannot take the logarithm of a negative number, and so this solution is what is called extraneous and is not a valid solution. So our only solution is x equals 3. Now, a word of caution. Here in our exponential equations, it is possible to have a negative solution. Don't confuse that with a logarithmic. It is not possible to have to take the logarithm of a negative number. So don't confuse those two. Somebody's going to do that. And I want to point out that this is the only one of these exercises that has an even numbered question as one of the practice exercises. And I just included it because I wanted as many as possible, as many practice exercises as possible, and this one looked like a good one, as I recall. Of course, if it's even, there's no answer in the back of the book for you, but I am happy to provide it. Now, in question 10, we have a continuously compounded interest, and for a principal of 10,000, and we want to know how long it's going to take to mature to 15,000 if the interest rate is 5%, and of course it's compounded continuously. Well, what is the time? Well, the time is up in the exponent, and the best way for us to liberate that variable from the exponent is to take the logarithm of both sides of the equation. To do that, we have to uncover the base, and we have to recognize that the base in this expression is e. So we divide both sides of this equation by 10,000 to uncover that base e. Well, 15,000 divided by 10,000 is 1.5. It's very convenient. And so then I take the logarithm, I take the natural logarithm of both sides of this equation. And so natural logarithm of 1.5 is what? I don't know, but it's some number. So just think of it that way. It's just a number. And when we take the natural logarithm of e raised to any exponent, these are inverse operations of one another. They undo one another, which is what we did here when we took log base 4 of 4 raised to some exponent. This is, those are inverse operations and they cancel out. And so here we have that same property, that same principle. Those two cancel each other out, and the exponent is now left on the right side of the equation. Well, now we just have a number is equal to a number times our variable, and we divide both sides of this equation by this coefficient 0.05, and log base, or a natural log of 1.5 divided by 0.05 is the time in question. And when we enter that into our calculator, we get 8.1 and then a bunch of decimals, but we round it, and we were asked to round to 2 decimal places, so we round to 8.11, and that's how many years it takes for $10,000 to reach $15,000 if it's invested at 5%.